All right, everybody, this will be the last two lessons of the semester. We're going to do 6.2 and 6.3. We'll do them in two videos. So the first one here, we'll do 6.2, which is called partial derivatives. Believe it or not, this is actually a topic that you would not normally get until Calculus 3. We are going to simplify it because there's quite a bit of things that happen in Calculus 3 that lead up to this. But the idea behind it is really not that difficult to do as far as the problems are concerned. There's a lot of math that goes into why everything is what it is, but that would take a very long time to explain. Ultimately, the general idea of this is that you kind of want to figure out how something changes if we assume that everything else, even if they're variables, are constants. And I know that's kind of an odd idea. Um, but basically, if you think about it in terms of something in real life, like, I don't know, maybe you're talking about how the wind affects how it feels outside. So you know that they have this thing called wind chill. Um, the temperature, the actual temperature outside affects how it feels, but the wind also affects how it feels. So the actual temperature is going to affect how you feel, but the wind that's actually coming through will also affect how you feel. Well, the idea behind this partial derivative is maybe we're saying that, okay, if we know that the wind is going to constantly blow at 15 miles per hour, how is the temperature, the actual temperature outside, going to affect how you feel if we know that the wind is always 15 miles per hour? We know that's not going to be the case. Can't just hold steady like that. But if we could, that's the idea. Or the other way around, how would the wind chill affect us, or how would the velocity of the wind affect how we feel if we know the temperature stays at 78 degrees constantly and doesn't move? So that's the idea of how this kind of stuff might work in real life. For this, we're just doing the math. So we're going to figure this thing out using some mathematics. So here's the idea. A partial derivative is a derivative with respect to only one variable at a time. There is a bunch of notation up here. I'm going to highlight the ones that are really going to mean something to you. Um, this one right here, or it might just be f sub x. This one right here, or just f sub y, and then z sub x. And it could be written as this thing right here, dz over dx. Notice the differences, though, in the d. And this is kind of an important thing. When we're talking about a partial derivative, you write your d without the stem. This is a d with the stem. This is a d without the stem. It's almost like a backwards 6, actually, is the easiest way to think about it. So that is a partial derivative notation. So instead of doing like dx, dy, or something like that, it would now be this notation. And that's probably one of the hardest things to get used to, is writing your d's without the stem. Um, but that is the partial derivative notation. And if I switch to something else, which I don't think that I will let you know. Most likely, we are not going to use this notation right here. We will use these. They're easier to figure out, but we will probably not use that notation right there. It's too difficult for us to worry about. And those are for second derivatives. I will explain as we go. All right, let's see if we can figure this out. The first one says I want to find dz dx. I want to find the derivative of z. Well, that's our function right here. I want to find the derivative of this thing with only taking the derivatives with respect to x, meaning that you treat the y's like they are just numbers. So y could be like 7. We treat it like it's just a number. So let's see if you can follow what we're doing here. dz dx. I'm going to take anything that has a x in it just like it's a regular derivative. So the 2x cubed is going to end up being 6x squared. The 3xy is a little bit different. Pretend like 3 and y are just constants. So if I wrote it differently, I would write it as 3yx. Group those two things together. If that 3y was like 15, the derivative of 15x would just be 15. Well, the derivative of 3yx, because the y is now just a constant, is 3y. And then minus the derivative of x, which is 1. That is dz dx. It also wants us to find dz dy, which means I'm going to take the partial derivative of z with respect to y. So now we treat anything that's not y like a constant. Well, 2x cubed, if we're only taking the derivative with respect to y, is just like a constant. The derivative of a constant is 0. So the 2x cubed part is 0. The 3xy part, well, the 3 and the x are now constants because we're taking the derivative with respect to y only. So that's like having a number out in front of y, so the derivative of that would just be that number, which is 3x. And then the derivative of minus x has no y's in it. It's constant. It's 0. It's gone. So there are my two partial derivatives. And then it wants us to find dz dx, and this thing means to evaluate that when x is -2 and y is -3. That's an ordered pair at the bottom. So it's just saying plug -2 in for x and 3 in for y and see what you get. Well, we already found dz dx right above us, so we're just going to plug -2 in for x and -3 in for y, and then we'll see what we get there. So that's going to be 6 times 4, which is 24. -3 times 3 is -9, minus 1. 24 minus 9 minus 1 should give you 14. And then on this one over here, it also wants us to find dz dy, but this time it wants us to find that at the point 0, -5, which means I'm going to plug 0 in for x and -5 in for y. I don't have a y in dz dy, so I'm just going to plug 0 in for x, and we get 0. All right, if the partial derivative thing is kind of like you're not quite understanding it yet, please go back and watch this part again, see if it makes more sense. Sorry about my notifications there. I am going to do my best to keep going with this, and hopefully you guys will understand the partials as we go. Once it clicks, I think it'll click with you guys. Just got to give it a little bit of time. So number 10 wants us to find both the partial of the partial of f with respect to x, that's what that means, and the partial of f with respect to y. It's two separate things. So the first one is f sub x, which means take the derivative of your function with only respect to x. Treat y like it's a constant. Well, you do have to remember how to do exponential derivatives, which is to rewrite the exponential, and then we multiply that times the derivative of the exponent. Well, the exponent is 2x minus y. The only part that has x in it is 2x, so the minus y part will be gone, and the derivative of 2x is 2. So really we can write that as 2e to the 2x, that's a minus y. And then f sub y means take the derivative with only respect to y. So again, it's exponential. It's the same function we started with, so we rewrite it. But now the derivative of the exponent with respect to y, the 2x part doesn't matter, so that's 0. The derivative of the minus y part is minus 1. So we can rewrite that simply as minus e to the 2x minus y. And you do have to remember how to take the derivatives exponentials. Likewise, in 14, we have to remember how to take the derivatives of natural logs, as well as potentially doing a product rule. Now, when I do the partial with respect to x, there's no x out in front of that natural log. The only x that occurs is in the natural log. So that y out in front is basically just like having a number 4 or something like that out front. It's a constant. So when I take the derivative, I just rewrite the coefficient, and then I have to take the derivative of a natural log, which is 1 over the argument of the natural log times the derivative of what's inside the argument. Well, we're only taking this with respect to x, so the derivative of x plus 2y is just 1 for x. The 2y is gone. It was constant. So I can multiply that times 1. And then if I want to clean that up, that would just be the same as y over x plus 2y. And then f sub y. Now this is a product rule because I have a y here and I have a y within that. So I do have to use the product rule here. So the derivative of y is 1, that's the derivative of the first term, times the second term, which is ln of x plus 2y. Plus, I do the derivative of the second one now. That's the natural log part. Again, it's 1 over x plus 2y times the derivative of the inside, because it's a chain. The derivative of the inside of that, x plus 2y, again, now it's only with respect to y, is 2. And then don't forget to multiply this times the first term. So let me kind of highlight some things here. This was the derivative of the first. So that's the derivative of the first one. This is simply the second term. This, all of this part, is the derivative of the second term, and then this was the first. So that's a product rule. Okay, and you can clean it up a little bit, but if you get to that, honestly, I would be very, very happy with that. Okay, then the last one. The last one, again, wants us to take f sub x and f sub y. So f sub x, the derivative of that expression on the right-hand side there with respect to only x. X is on the inside of the parentheses, so it's a chain rule to start. Bring the 2 out front and multiply it by the 3. Rewrite the inside. Reduce the power by 1, so now it's to the first power. But then don't forget to multiply it by the derivative of the inside, and since we're taking the derivative with respect to x only, everything else is constant, so the derivative of the inside with respect to x is just 2. So then you could write that as 12 times 2x plus y minus 5, just multiplying the 2 and the 6 together from the outsides of the parentheses. I could distribute that 12 into the parentheses as well. I'm just not going to bother doing that in this case, but you could. F sub y, taking the derivative now with respect to y. Again, the y is on the inside of the parentheses, so we'll bring the 2 to the front. It's still a chain rule. Rewrite the inside. And then multiply that by the derivative of the inside, but now it's only with respect to y, so the derivative of the inside part with respect to y is just 1. So really that one's going to be 6 times 2x plus y minus 5. All right, again, if you are having problems with any of these things as far as what you're taking the derivative with respect to, it's just taking the derivative with respect to one of the letters. The other letters basically are just like numbers. Treat them that way. When you take the derivatives of them, they're 0, they're gone. In the number 26, now we have a function of 3 variables, not just 2. So this one becomes a little bit more complicated. In all honesty, what I would probably do here is I would go ahead and distribute this into everything in the parentheses. And just in case you're not sure what that letter there is, it's the Greek letter lambda. Yeah, it's just the Greek letter lambda. I don't know what else to tell you, but that's what it is. So it's just another variable. All right, so I'm going to rewrite this expression off to the right-hand side here. So it's x squared minus y squared. Now I'm going to distribute that minus lambda into everything. So it'll be minus 4x lambda plus 7y lambda. and then plus 10 lambda. So now I want to take the partial derivatives. I've got 3 of them to do. The partial with respect to x, the partial with respect to y, and the partial with respect to lambda. The partial of this thing with respect to x, I'm going to go from the blue thing that I put on the right-hand side here. I am just taking the derivative of stuff that has x in it. Everything else is constant. So the first one is 2x. The second term where I have minus y squared, that's a constant. It goes to 0. The third term has negative 4x lambda. It does have x in it, so everything that's not x is the constant, so the derivative of that would be minus 4 lambda. And none of the other stuff has x in it, so that's done. Everything else would have a derivative of 0. F sub y. Only take the derivative with stuff with y's in it. If it doesn't have a y in it, it goes to 0. So x squared goes to 0. Minus y squared, the derivative of that is minus 2y. Minus 4x lambda, no y's in it, it goes to 0. Plus 7y lambda, that has a y in it, so the derivative of that will be plus 7 lambda. And then the last one, 10 lambda, does not have y's in it, it goes to 0. So that's your partial with respect to y. And then the partial with respect to lambda, I've got a bunch of these. The x squared, the minus y squared, those are 0, no lambda. The last 3 terms all have lambda in it, so it's minus 4x lambda, so that's going to be minus 4x. Plus 7y lambda, the derivative of that is plus 7y. And then plus 10 lambda, the derivative of that is plus 10. And those are your 3 partial derivatives with respect to all of the variables, x, y, and lambda. All right, just like all the other stuff that we did, you can also take second derivatives. They're written just a little bit differently. In order to take second derivatives, just like you would before, you have to find the first derivatives. So we'll start with that, and then I'll show you what the rest of this is going to look like. It's quite a bit more. It actually says find the 4 second-order partial derivatives, and I'll show you why that is in a second. All right, so the first one, we're going to do the derivative partial with respect to x. So the first term's got x to the 4th y cubed. Again, treat the y cubed like it's a constant. So just take the derivative of the x part, which is going to be 4x cubed. Still got to multiply it by the y cubed because it's part of it. That's just a constant. And then the second one is x squared y cubed. So take the derivative of the x part. That's 2x. And then the y cubed is like a constant. So there is your partial with respect to x. Now I'm going to do the partial with respect to y. Same general idea. Treat the x to the 4th like it's a constant, but the y cubed you take the derivative of. So bring the 3 out to the front, keep the x to the 4th, but then y now gets raised to the 2nd power. Reduce the power by 1. And then the same thing, excuse me, same thing with x squared y cubed. X squared stays there. Bring the 3 from the y out to the front and reduce the y by 1. So there is the partial of x and the partial of y. Now it says to find the 4 second-order partial derivatives. Second-order partial derivatives mean I need to take the derivative again of x with respect to another x. So it's actually f sub xx. It just means take the derivative again with respect to x. Okay? So if I take the derivative of the first part with respect to x, we bring the 3 from the x out front and multiply it. That's 12. Reduce the power by 1. Keep the y cubed, it's a constant. Minus, taking the derivative of the second part with respect to x, it's only x to the first power, so what's left over is 2y cubed. That's fxx. Do the exact same thing with the y's, fyy. So now I'm going to take the derivative of this one with respect to y again. Bring the 2 from the y out to the front, 6x to the fourth, reduce the power of y by 1. Okay, do the exact same thing with the second term. Bring the 2 from the y out to the front, keep everything else, reduce the power by 1. That is called the second order partial derivative with respect to x and y twice. But there are other second order partial derivatives. I didn't have to do the derivative of x twice. I could have done the derivative of x, which is what I have in blue, but then with respect to y instead of x, which means I'm going to go from this one right here, but I'm going to take the derivative of that now with respect to y. And watch what happens on this. So if I take the derivative of the blue part with respect to y now, I'm going to bring the 3 from the y out front. Oops, it's not 3. It's going to get multiplied by that 4. Give me 12. The x cubed stays the same, but now the y gets reduced by 1. And then I'm going to bring the 3 from the second y out to the front and multiply it. So that's minus 6. Keep the x, reduce the y by 1. Okay, nothing too terribly interesting there yet. Now I'm going to do fy sub x, which means I'm going to go from this one, but now I'm going to take the derivative of the green one with respect to x. So basically I'm just switching the variables. So now with respect to x, that first term, I bring the 4 from the x to the front and multiply it. That gives me 12x, reduce the x by 1, keep the y. And then I'm going to bring, because I'm doing this with respect to x, the 2 from the x out to the front and multiply this one, reduce the x by 1, keep the y. What you should notice is that this is exactly the same as this. Okay, there's actually a theorem, which you don't really have to know the theorem by name, but the theorem is called Clarets Theorem, and it just says that the second partial derivatives are equal to each other. And that's if you do fxy and fyx. So you've got to go with both variables. And that should be the case. All right, moving on to number 40. So this time we are given x, ln, y, and we basically want to find all 4 of the second order partial derivatives, just like we did. So in order to do that, we have to find the first derivatives first. So fx, the derivative of that with respect to x, the ln of y is a constant, so x times ln of y, the derivative is just ln y. Fy. Now the x is constant. Take the derivative of natural log of y, keep the x, which is 1 over y. And I'm going to rewrite that as x over y. It's the same thing. Now I need to find all the second order partial derivatives. So I'm going to do fxx first. That's the easy one. The derivative of the fx with respect to x, again, there's no x's in it. So it's like a constant. The derivative of a constant is 0. That one's actually really nice. The one over here, fyy, I actually do have something to do because I've got x over y. So really that's the same thing as basically a quotient. But the top is a constant. So when I do the derivative of using the quotient rule, the derivative of the top is 0 times the bottom. Minus the derivative of the bottom, the derivative of y is 1 times the top. All over the bottom squared. Well, if I simplify that, that's going to be 0 times y, that's 0, minus x, so that's minus x over y squared. Okay, now I need to do my other second partial derivatives, which is where you include both variables. So this one I'll do fxy. So I'm going to go back from this one and take the derivative with respect to y. The derivative of that with respect to y, it's a natural log of y, so it's just 1 over y. And then I'm going to do fyx, so I'm going to go from that one and take the derivative of that one, excuse me, with respect to x this time. You can use the quotient rule. You can do it a different way. I'm going to show you the quotient rule because I figure that's the way most of you guys are going to see this. So the derivative of the top now, that's x. So the derivative of that was 1 times the bottom minus the derivative of the bottom. Since we're doing this with respect to x, the derivative of the bottom is 0 times the top over the bottom squared. Simplifying that, we get 1y minus 0, so that's just y over y squared, but one of the y's is going to divide out, so you end up with 1 over y. And these are the same, and they should be. All right, I'm hoping that we're okay so far. Again, if not, please slow this down, go back, watch it again, see if you can figure everything out. We've got one more problem to do, and this one's going to be a little messy as far as the numbers are concerned, but remember, you're allowed to use your calculator to plug stuff in. Because I even tried doing this stuff by hand, and it got messy for me, and I was just like, yeah, let's just kind of use our calculator for this. So what we have is we have Lincolnville Sporting Goods had the following production function for a certain product. It says that P of xy equals 2400, x to the 2/5, y to the 3/5. Where little p is the number of units produced with x units of labor and y units of capital. Find the number of units produced with 32 units of labor and 1024, that should say units, not unites, of capital. And we also want to find the marginal productivities and evaluate at x equals 32 and y equals 1024. So the first part, part A, is really simple because all it's asking us to do is plug in 32 units of labor and 1024 units of capital into the P function. So really part A is just looking for P at 32, 1024. So that's really all that that's asking for. So let's go ahead and plug that in. That's going to be 2400 times 32 to the 2/5 times 1024 to the 3/5. Now again, that stuff can be done by hand, but there's really no point in doing all that. It's a lot of big numbers to multiply out. So go ahead and plug that in your calculator and see what you get. All right, go ahead and pause it if you have to, and then come back in a second. Okay, hopefully you paused it, and the number you should have gotten here was 614,440. That would be the number of units produced. Part B is asking us to do a little bit more. It wants to know the marginal productivities evaluated at x equals 32 and y equals 1024. Remember that marginals are derivatives, which means because I have two variables here that vary, they're both independent variables, we need to do the partials, which is obviously the section that we're in. So what I need to do is I need to do p sub x, and I need to do p sub y, and I need to evaluate both of those at the x and y values that they gave me. So the first one, p sub x, it's taking the derivative of our function with respect to x only. So we bring the 2/5 from the x out front and multiply it by the 2400. So that would be 2/5 times the 2400. And since we're going to use a calculator, don't worry about simplifying that right now if you don't want to. Reduce the power of x by 1. So 2/5 minus 1 is negative 3/5. Keep the y the same. It's a constant. And then I need to evaluate that at 32, 1024. So we're going to plug that in. 2/5, 2400. So that would be what, 32 to the negative 3/5 power times 1024 to the positive 3/5 power. and then we're going to figure out what that gives us. I will pause mine, you pause yours. It won't seem like I'm gone for very long, but go ahead and pause it and come back in a second. All right, assuming that I plugged everything in correctly, and hopefully you guys will find any mistakes if I make them. I got 12,802.89 rounded. So that would be the marginal productivity per unit of labor. So in other words, if we're only seeing how the units of labor changes things, if we keep the amount of units of capital constant and just change the units of labor, this is how it would change things. So now let's see what p sub y would be. That would be taking the derivative with respect to y only. So bring the 3/5 from the y to the front. Multiply it by the 2400. Keep the x the same, but reduce the power of the y by 1, so that would now be to the negative 2/5. And then I need to figure out what the marginal is at 32 and 1024. So again, let's plug that in. So we get 3/5, 2400, 32 to the 2/5 power, and 1024 to the negative 2/5 power. And that should give us, again, go ahead and pause it and come back, and I'm going to do that same thing. All right, and I get 256.0, looks like 6 rounded. Assuming I plugged everything in right. Looking at these numbers, I'm not quite confident that I did, but hopefully you guys will figure out if I made any mistakes there plugging something in. Everything that's written up there should be correct as far as that's concerned. But that is it. That is partial derivatives. You will need to be able to do partial derivatives for the next section as well, which is going to be another application, which is finding maximums and minimums in multiple variables, not just 2 variables. All right, I will come back with one more video and we'll be done.